Okay, welcome back everyone. Calculus 3 class notes here in section 15.8, and we're on example 95 on page 107. So remember, this section is about going through understanding how the Jacobian is helping us to do the transformations. So this is a more mathematical approach to doing transformations, or essentially doing substitutions in multiple integrals. But when we say the word substitution in multiple integrals, we don't want to think of it typically as the typical U substitution for a single integral, other than the ideas there are similar. But the bottom line is we are transforming the entire integral at once to some other coordinate system. Okay, so in this example, we're going to evaluate the double integral from 0 to 4 with respect to y, and then from y over 2 to y over 2 plus 1 with respect to x of the function 2x minus y over 2. By applying the transformation, that I'm going to let u equal 2x minus y. Now think of this as substitutions, right? So I'm letting u equal this function, and then v would be the y over 2 here, and that will help us transform this function into a uv integral. Now actually there's no problem with integrating this one straight out, so I wanted to do it real quick. I don't think I need to explain that to you at this point, but I just integrated it straight because this is not a hard function to integrate, and I could see that the answer was 2. So let's go ahead and sketch R. So y goes from 0 to 4, and as y goes from 0 to 4, x goes from the function y over 2, which is the same as 2x, to the function y over 2 plus 1, which is the same as y equals 2x minus 2. Okay? So with the coordinate transformation, now what I need to know is what x equals and what y equals in terms of u and v. So I'm making the substitutions that u equals 2x minus y over 2 and that v equals y over 2. So that's a very simple system of equations to solve, especially since the second equation only involves y and v. That tells me that in terms of v or u, y is equal to 2v. Once I know y is equal to 2v, I'll take that back up in and plug it into this equation, which tells me that 2x is equal to 2u plus 2v, so x is equal to u plus v. So this is what x and y are in terms of u and v. So that's part of the problem. The next part is I need to understand what are these boundaries here in terms of u and v. So the best way to do that again is to make this table. So I'm going to write the xy equations for the boundary of R. R is the region in the xy plane. So x goes from y over 2 to y over 2 plus 1. So those are the two boundaries there as y goes from 0 to 4. So y goes from 0 to 4, easy to solve because y is 2v. So 2v equals 0 is the same as v equals 0. And 2v equals 4 is the same as v equals 2. So y going from 0 to 4 transforms to v going from 0 to 2. And then up here I got a tiny little bit more algebra, but x is u plus v, so u plus v is equal to y, which is 2v divided by 2. In other words, u plus v equals v. Subtract v from both sides, and I see that that means u equals 0. And then if I have u plus v equals x equals y over 2 plus 1, that means u plus v equals 2v over 2 plus 1. So u plus v equals v plus 1. Subtract v from both sides, I see that means that u equals 1. So these are the simplified boundary equations transformed. These are actually transformed into the xy boundary equations, but when we do these problems, we think of it backwards. So that means I have the very simple sketch of G, the region of integration in the UV plane. So the last thing I need to do then is to compute the Jacobian. So the Jacobian, remember, of u and v is the partial of x respect to u, partial x respect to v in the first row of a 2 by 2 determinant, partial y respect to u, partial y respect to v, a second row of the 2 by 2 determinant. So these are simple partial derivatives. I get 1 and 1, 0 and 2. That determinant comes out to be 2. So how does this transform? So this original integral, so this becomes u. There's my u. The dx dy becomes the Jacobian of u and v times du dv. So the Jacobian of u and v is 2, the absolute value of the Jacobian, but the absolute value of 2 is 2, so I just plug in 2. And then my u goes from 0 to 1 and my v goes from 0 to 2, that's from the table. Very simple integral to do. Integral of u 2u with respect to u is u squared. Evaluate from u equals 0 to u equals 1, that gives me 1. Integral of 1 dv is v. Evaluate from 0 to 2 gives me 2. So there's the answer that we got. This is a much simpler integral to do, although the first one was not that hard. But it does demonstrate to us how we can make these substitutions and use the Jacobian as sort of the equivalent of that g prime of u in the single integral case.